Let's say we toss two dice and we add together the faces that show when they land. We could expect outcomes that look like 2 and 4. So we can see that in our table, 2, 4. That would represent the outcome of one dice being a 2, the other dice being a 4. We could have other outcomes like 1, 5, 4, 1, 6, 3. So we can represent the entire sample space here of our experiment in the table using ordered pairs, where the two numbers inside of the parentheses represent the face value on each of the two dice that we get from each dice roll. We're actually more interested in the sums of these faces than we are with the individual values. So for every outcome that we see in this table, we want to add together the two numbers in the parentheses. So for the outcome 2, 4, that has a sum of 6. And for the outcome 1, 5, that has a sum of 6. Outcome 4, 1, that has a sum of 5. And then the outcome 6, 3, that has a sum of 9. So we're going to replace all of the specific outcomes where we're seeing the face value of the two dice. We'll replace those with their sums. So now we can see that there's multiple ways to get a sum equal to 5. However, there's only one way to get a sum equal to a 2, and there's only one way to get a sum equal to a 12. So if we were to roll two dice and expect an outcome, maybe we don't expect to get a sum of 2. It's not very common. Or maybe we don't expect to get a sum of 12, because that's also not very common. But notice that there are a lot of 7s in this table. That's a very common outcome. We expect a 7 to happen a lot of the time, and that's because there's so many different ways to get a sum that results in a 7. So if we were to say, what do you expect to get when you roll two dice and add together the faces? Intuitively, we might say 7. But we want to talk about a way to quantify that using a calculation. And that calculation will be expected value, the long-term average. We can make a probability distribution table to keep track of the various probabilities for each of the possible sums that we get from rolling two six-sided dice. So if we look, we can see that there's one possible outcome that gives us a sum of 2. And there's 36 total possible outcomes in the experiment. So we know the probability of getting a sum equal to 2 is 1 out of 36. There's 2 ways to get a 3, so that probability would be 2 out of 36. 3 ways to get a 4. And we can go all the way through the table, filling out the probabilities based on how many ways we can achieve each sum, and then putting that as a fraction over 36 for the total possible outcomes. And before we move on, let's double check. Are we looking at a probability distribution function? Well, we need to make sure that all of our probabilities are between 0 and 1 inclusive. And they are. We have no negative numbers in that probability column. We also don't have any numbers that are larger than 1, so far that looks good. But also we need to check that the sum of all of our probabilities equals 1 exactly, no more, no less. So if we add up all of these green fractions in the probability column, we need to check that it equals 1. It does. Make sure you verify that for yourself. We've confirmed we're looking at a probability distribution function because it meets both of the criteria. All of our probabilities are true probabilities, and the sum of all of our probabilities totals to 1. So we definitely are working with a probability distribution function. Now that we've confirmed we're looking at a probability distribution function, we can start to talk about the average value of this probability distribution function. Rolling a dice once is not representative of an average. So maybe we roll 2 dice and we get 6 and 2. That sum is an 8. This is not a representation of the long-term average. If we had rolled the dice maybe 10 times, it's getting a little closer. We could calculate on average what the outcome of these 10 rolls is. But notice that the variability from one roll to the next it's not really matching up with the theoretical probabilities that we have determined for each of the possible outcomes. The theoretical probabilities are represented in this picture as the histogram in the background. So the outline of the histogram matches the theoretical probabilities that we calculated just moments ago. If we only do this experiment 10 times, our experimental probabilities do not match up perfectly with our theoretical probabilities. And this is the law of large numbers. We need to repeat the experiment many, many times in order to see the two things converge, meaning that they start to look identical to each other. After 110 rolls, we're getting a little closer, but we're still not really lining up. 510 rolls, looking a little better. Not until we get into the tens of thousands of rolls do we start to see visually that our experiment and our theory are converging. And this is the idea of the long-term average. So we need to make sure that we're not using expected value or long-term average to represent one trial of an experiment, but rather that it represents the average over many, many repetitions of the experiment. Now let's go ahead and calculate our average. So we understand our average represents the long-term average here, and the calculation for that involves multiplying each of our variable values to its corresponding probability. So the variable value 2 gets multiplied to the probability 1 out of 36, and we're going to repeat that for each variable with all of their corresponding probabilities. Next, we're going to add up all of these products. The sum of all of the products, x times p of x, gives us a fraction that reduces to the value 7. And if we look at our experiment that has been ran thousands and tens of thousands of times, we can see that our average, 7, represents the center of this data set. This long-term average of the experiment is known as the expected value, or the mean. We use the Greek letter mu to denote this value. The standard deviation of a PDF tells us how far away a single variable value is from the average, from the expected value or the mean of the experiment. And we use the Greek letter sigma to represent our standard deviation.